I'm a postdoc at UNSW Sydney, and although this is my first SEL4 summit, I've been in and around the work of the group for quite a while, especially in the last 10 years when I came back to the group in 2014 to pursue a master's, because by that time I had been working for a Go-Not startup for several years since my undergraduate years, and through its acquisition by General Dynamics and getting closed. And by that point, I had become very curious about how formal methods can be done on systems in and around microkernels, which I had been working with at that job. So, and that's basically been the focus of my career in the last 10 years. So with that, today I'm going to present the status of a couple of verification efforts at the UNSW Trustworthy Systems Lab surrounding the OS perspective on time protection, which Neil's just told you a little bit about the hardware side of, and also the verification of OS services that'll run on top of SEL4. Okay, so in previous summits and possibly previous talks in this summit, you may have seen a diagram like this that is about the structure of the verification of the SEL4 kernel. Okay, and so we have various properties of interest, such as confidentiality, integrity, availability, that are proved on top of an abstract model, and a functional correctness proof, which is in the sense that the C implementation is a correct implementation of the functionality of the abstract model by refinement. And we have a similar refinement argument saying that the binary code is correctly translated by the compiler. Okay, so of course it's the world's first OS kernel with this kind of proof about it, and these proofs are machine checked. And well, at least the ones all the way down to the C implementation are machine checked using Isabelle Hull, an interactive theorem prover, whereas there's a more automated step for the translation validation. Okay, so if we just kind of focus on a few aspects of this, there's much more to do, right? Because what we want to be able to do is prove further properties of the kernel, and so where they follow the proof structure that we carry properties down via refinement and get the properties we proved about the abstract model. We similarly want to do this for a property called time protection, which implements protection against timing channels between users running on top of SEL4. Okay, so this frontier is downwards, okay, because we'll need to prove something about the abstract spec and its preservation by changing what refinement means. Now, that's one of our ambitions for the kernel. I haven't mentioned multi-core, but I'm sure you know that there's other efforts there. And on the user side, we want to push assurances up into user land as well. Okay, because the kernel on its own is not enough to implement a correct and secure system. We need to be able to say something and gain assurance about the whole system. So what have we done so far? We've got a library and which provides this abstraction that has less footguns than the raw SEL4 spec called the Microkit. And from here, we want to be able to build operating system services that are trustworthy. We place our trust in them, and therefore we need to make sure they're trustworthy. And this frontier is upwards, okay, because we're trying to determine formal methods that are applicable to the user land systems on top of SEL4, okay? So these are the two frontiers, and our ambition would be that we can gain some assurance about whole systems running on top of SEL4, right? Okay, so where are we on that? Focusing on the efforts that are happening at UNSW. So first I'll focus on the userland story, because that's where we happily have more progress to report in recent times. So the very first step builds on top of a result that we achieved early, which was the verification of the Microkit library using an SMT solver-based approach, okay? Now, what we realized, though, is that there is a gap between the interface provided by the kernel, between the behavior of the kernel as assumed by that Microkit spec, and what we've actually proved about the microkernel. So although the abstract model of SEL4 specifies what the kernel is doing in between the kernel entry and exit, the form of the properties assumed about certain system calls called by the Microkit come in the form of a Hoare triple. Okay, basically that, okay, well, if my Microkit library ensures these preconditions when it calls a given system call, then we just assume that the system, that the SEL4 kernel will return to us with these postconditions satisfied. Okay, so these Hoare triples are what are the interface assumed of the system calls called by the Microkit, but we should prove those Hoare triples, right? So at the moment, we don't have those kinds of proofs, and so why don't we go about proving them? Well, in some cases, this is straightforward, okay? And I've put a little hard hat to show that so when I say straightforward, I'm not trivializing the task here. This is some good, solid proof engineering, but this is using formal techniques that we already know about. Okay, these are ones that we know how to do. And in this case, let's say somebody calls SEL4 receive, and there's already a message waiting, or already a notification waiting to be received, and it'll return immediately. Okay, so you can prove a Hoare triple over the abstract spec because you know that you're returning to the same userland process that called the kernel. Okay. Now, the tricky case is when we block. Okay, so say SEL4 receive is called, but there's nothing waiting. There's nothing, to receive at that moment. Then the OS kernel will not return to that same user. It'll return to someone else. Okay, and so any number of other user processes may then be scheduled, right? And you can have any number of entries and exits to the kernel in between until finally the one system call, SEL4 call or SEL4 send, happens to wake up the original caller, all right? And then we have to prove a Hoare triple that spans all of those things happening, right? So it turns out that this case is not actually well studied, or at least not in the literature. It hasn't been handled, it doesn't seem to have been handled by prior OS verification work, which makes it research. Okay, so we'll have to figure out what to do there, and I have some ideas, and ask me in 2 to 4 months, and we'll see if we got there with it. And the closest thing I found was a Certicos paper where there is some blocking, but it's on I/O, not on the actions of other users. Okay, so that's under investigation now. So that's the part I'm reporting on that I'm most closely involved in, and now I'm going to report the work of others in progress. So that was the story of the interface between the two, and we also want to prove things about the systems running on top of SEL4. So this is kind of a very vague schematic, but you've seen a few concrete examples of what these systems might look like throughout this summit. And so as a particular example, we're focusing on the Ethernet virtualization architecture for Lions OS, which is based on the SEL4 device driver framework. And in our instance, we're running it on top of the Microkit. And you notice here that there's a division between untrusted and trusted user processes, okay? Because we don't trust the clients at all. They could do anything, and they're not part of the trusted computing base. But here, we're also providing components that we trust, okay? And because they're trusted, that justifies their verification, okay? To make them trustworthy. So what are we doing on this front at UNSW? Well, there's 2 areas to focus on. The first that I'll talk about is the method of communication between the components. Okay, so I've depicted these as this diagram depicts these as these rings, just because they happen to be implemented as ring buffers. These are queues, single producer, single consumer queues. And so far, you'll have heard Courtney's talk about how she used Spin and Promula to verify that aggressive optimizations to the operation of these queues do not deadlock. Okay, so that's something we've done so far. And what's currently under investigation as of recently is whether we can use deductive verification-based methods or possibly other methods if the current SMT-based methods aren't powerful enough to verify the correctness of the queues under weak memory, which would be relevant to multi-core. Okay, so that's one side. And as for the components themselves, we also want to verify some properties. Okay, so here we're targeting the components like the virtualizers, copy component, but our biggest focus at the moment is on the Ethernet driver. And we've got two approaches running in parallel. Sort of Gernot wanted to race the two approaches and see what we get out of them, comparative power and ease of use. So on one side, we've got a deductive verification-based approach in which we are translating Pancake to the Viper intermediate language. And that is a framework, an intermediate language that acts as a front end to various SMT solver-based backends. Okay? And in parallel with that, we've got an interactive theorem proving based approach using Hall 4, which is the native proof language for the Pancake compiler. And Miki Tanaka talked about a bit about that yesterday. That's where that may potentially, we expect that to be potentially more expressive as a payoff for the extra effort, because we've got a slightly more sophisticated semantics in the form of interaction trees. So we'll see how that goes. And the time frame for that is next month. So ask me in a month or two. Okay, so the sorts of things we want to prove are various notions of functional correctness. But in addition to that, we're also finding that we are figuring out appropriate ways to model the non-determinism coming from the behavior of the device, right? So that we can explore all the paths of the driver properly. And so that's part of the investigation. And this will feed, hopefully, we hope this to feed into another project that hasn't quite started yet, but is lined up on hardware verification of the devices themselves. Okay, so hopefully our formal methods work will help, our software side formal methods work for the drivers will help inform the interface that the hardware verification projects might target. Right, so that's almost it, but that's not the whole story, because at the end of the day, we want to have assurances about the whole system, right? So this is probably the broadest of the arrows here, because there are very many ways to go about this, depending on what sorts of properties you want to target. So for functional correctness, we have an honors student in the audience, Matthew here, who's looking at this, looking at ways to compose specifications of communicating processes on top of SEL4, on top of a generic kernel. But there's plenty of research to do here, especially if we want to extend our ambitions to security properties. Okay, so we haven't begun that yet, but I have a bit of background in compositionality of confidentiality properties, which is what I did for my PhD, and hopefully we can develop a story there with some enthusiastic students. So I'll switch gears now and talk about time protection. Okay, so what is this time protection property we want to prove about the kernel? Well, it's a security property. And it's stronger than most security properties because whereas the OS has historically implemented something called memory protection, which says, look, if I'm a spy, I cannot simply read memory that I don't have access to, right? So it's not even mapped. I can't access it. If I try to access addresses that aren't mapped, I get that doesn't work for me, okay? But unfortunately, even if memory protection is implemented, there is a way in which these two can talk to each other. Okay, so imagine that you've got the Trojan here, which has access to some secrets, and they're trying to exfiltrate that data to the spy. Well, they can do this without even having any mappings to each other's memory, because even if the spy accesses only their own memory, there's microarchitectural state that's shared between the two. And if the OS hasn't been very careful about which physical addresses is given to each of them, they can overlap in the cache. Rather, the cache can service the same physical addresses. So when the Trojan accesses its own memory, sorry, this was supposed to say that that normally the first time you access memory, it's loaded into a cache and it's slow and then it's fast. And then if the Trojan is possible, then if the OS has allocated physical memory carelessly for the Trojan to access its own memory, and for the spy to be able to tell that that's happened, okay, because it's evicted the relevant entry for the spy. Okay, so using a principle like this, anyone can talk to anyone, regardless of the security policy of the system. Okay, so that's no good. So Nils has already talked a bit about this. There's a general approach to this, to implementing time protection, which is to partition what you can and flush what you can't. Okay, so for caches further away from the cores, it's feasible to partition them. For the OS to be careful about what physical addresses it gives to each of the processes so they don't overlap in the cache. And as long as we have the right hardware primitives, like the fence.t implemented by Nils and co., then we can flush non-architected state on core and even determinize the amount of time that a flush takes. Okay, determinize the time at which we return after the flush. So here, what I mean by flushing is determinizing the state by effectively writing some deterministic value, and by padding, I mean waiting up until a fixed time. Okay. All right, so the SEL4 OS kernel's enforcement of time protection was first implemented by a PhD student named Chan Ge, with a result in 2019 on ARM and x86. Okay, and so since then we've ported that to RISC-V, to the CVA6 board that Nils spoke of last talk, and we wrote about that in a preprint that we put up on archive, this is all with the help of the hardware support provided by Nils. But that was all empirical. Okay, so both Chan's work and what we reported in archive is making sure that these things work empirically. We spoke a bit about in the preprint about how we would want to go about proving formally in the OS that it holds, and that's what the rest of this talk's going to be about. So what's the verification status of the operating system implementing time protection? Well, we need to prove a bunch of stuff, and if we kind of stretch out this structure here, what we have done so far is characterize formally what it does mean to implement time protection. Okay, so we formalized the security property, and we published that at the Formal Methods Symposium in 2023, and it's been defined for operating system kernels in general. And what we need to do now is instantiate that with the SEL4 kernel model, and we want to verify that it holds for the abstract spec. Now, what does that look like? Well, this is the actual structure of the proofs as Isabelle sessions in the SEL4 proof base, and you can see we've got the abstract spec, invariants proved about the abstract spec, and these are dependencies, by the way. And then the access control security proofs are built on top of that, and info flow is built on top of that. Okay? And relative to a generic non-interference theory, which we already modified to characterize time protection. And that's a whole bunch of very solid proof engineering. Okay? Because in our preprint, we laid out what we think is the approach, and we've already updated the abstract spec to add extra bookkeeping to try to keep track of some safe over-approximation of the addresses that are accessed by the kernel. Okay, because we want to then show that safe over-approximation of what's touched is a subset of the addresses that the security policy says the domain is allowed to access. And that configuration should reflect the correct coloring, the correct careful allocation of physical addresses so they don't step on each other in the cache. Okay, so what's the status of this? Well, a whole lot of proofs are broken because we added new machinery to ASPEC, and machinery that assumed that nothing would change is now getting changed by this ghost state that we added. Okay, so there's a whole bunch of engineering to fix those, to adapt and apply the proof engineering machinery, and we're about halfway through. And from there, we want to go down, okay? Because we need to update the notion of refinement so that we can carry this time protection property down to the confidentiality property proved at the bottom. So what does that mean? Well, again, there's actually more detail because there's this Haskell spec in the middle, which is still around for legacy reasons. This was at the panel they talked about how it was very good for getting the two teams to talk to each other. It still exists, and we need to push the property down through all the layers. And we also think we have an approach. We're going to preserve this subset relation, and if we can prove that the touched addresses down here is a subset of the ones up there, then we should be able to carry the property down. So that was in our archive preprint, but this is all very hand-wavy because we haven't done it yet. Okay, and of course, there's also, you can immediately see this is modular, some notion of the touched addresses set, given that we don't know what all the addresses are until we get down to the bottom, because there's some objects that are sort of kept track of up here, but we don't know the addresses until we get down here. So this is subset modular expanding what we know about the addresses. But that's the approach that we want to take. And that part has been stalled for a while, but we hope with some new, the funding outlook looking a bit better, potentially, that we can hire some people. So if any of this seems interesting to you, or you know anybody who would be up for this kind of proof engineering challenge, then get in contact. Right, so everything I've talked about so far is for a separation of kernel policy. This is a restrictive policy that allows nobody to talk to each other. Okay, where the policy has, no communication is allowed between any processes on top of the kernel, but there are going to be realistic systems where we want there, for example, to be data diodes, right, where there's unidirectional flow, but not in the reverse direction. So that means that there's some extra work for implementing these sorts of primitives, communication primitives, in such a way that doesn't allow a back channel via timing channels. So that's scope for a systems PhD thesis. We don't have anyone yet for that, but that would be the right scope for that, and in collaboration with possibly at least one systems and FM supervisor to make sure what they're doing is verifiable. Okay, so that's the overview of these two areas. And that's not all the research that's going on at UNSW, but in these two areas it is. There's also some multi-core research, and happy to have a chat about any of it. Okay, and this is the group.
Thank you, Rob. Questions?
So you want an axiomatic semantics for the kernel that deals with the blocking case, right? Where you don't have immediate return. This is the whole logic, right? You want your whole triples to work with the case where, and your example was receive blocks.
Yep.
Yeah.
So, but what do you mean by an axiomatic semantics?
Whole logic, whole triples.
Oh, okay.
Axiomatic
semantics,
yes. Right?
Sure.
So that should absolutely be doable, right? Once you get your operational semantics right.
Yep.
Like if you build it on top of an operational semantics that works, then you should be able to get like rely guarantee there.
Yeah. So
right, that should absolutely work, right?
Yeah, the approach I have in mind is rely guarantee based.
Yeah. Okay. Yeah. Well, let's talk about it because
okay,
that's totally doable.
Definitely.
So for the padding approach,
I assume you need an upper bound for the worst case execution time
Yep.
of the kernel, and to have that not impact performance too much, you don't want that to be too gratuitous, right? What do you need in the contract with the hardware to hit to know that sweet spot, and do you have that?
So you do need a worst case execution time analysis, and then you should configure the primitive that's going to implement the deterministic weight to that worst case execution time. So, Kernel, did you want to say something about that?
It's not that difficult as it sounds, because it's not arbitrary kernel worst case execution time. It's really the worst case latency of these hardware operations which you need, which is basically dominated by the dcache flush, because that has a variable execution latency. All the others are constant time. So it's not rocket science.
Yep.
I'll just get our next speaker to swap laptops over. Any other questions?
All the proofs you mentioned apply to closing the data info channel, but what are your plans to stop instruction cache info channel?
Sorry, can you? So was the question about closing?
Yeah. So all the proof things applies to data accesses, but you can also leak information through instruction cache.
Yeah.
usage.
So the instruction caches on core are flushed because so the on core state is flushed, and then we just partition the L2 and L3 if it exists.